So the problem in the book that I will be answering is problem 19 from the homework, chapter 4. And it was a pendulum is swinging back and forth, but the string attached is a spring with a spring constant K. So to start off, I started by thinking about the kinetic energy and how it would be 1/2 of ml dot squared. And then I was thinking, because it is going to be moving around in part of a circle, that it'd be easier to use polar coordinates. And then for the potential energy, I thought of it about the potential energy is equal to minus potential energy from the spring plus the potential energy from gravity. So to write that, it was U is equal to negative 1/2 K of L minus LO squared. And for some reason I forgot to write it, but plus mgy, where y here is equal to L cosine theta. And the kinetic energy rewrote in terms of spherical or polar coordinates is 1/2 of ml dot squared plus 1/2 of ml squared theta dot squared. And the potential energy is U is equal to negative 1/2 K of L minus LO squared plus mgl cosine theta. So putting that all together, where the Lagrangian is equal to T minus U, the Lagrangian is equal to 1/2 of L dot squared plus 1/2 of ml squared theta dot squared plus 1/2 of K of L minus LO squared minus mgl cosine theta. So then to find the motion for different for L and for theta, the Lagrangian, to solve it, the left-hand side is the partial derivative of Lagrangian with respect to L is going to be equal to d over dt of the partial derivative of the Lagrangian with respect to L dot. So for the left-hand side of the equation, the partial derivative of L with respect to the partial derivative of the Lagrangian with respect to L, that's going to be hitting this term, and this term. So when you take the derivative of those three terms, you get ml theta dot squared plus mg cosine theta minus kl minus lo. And then taking the partial derivative of the Lagrangian with respect to L dot, you see that only hits this one term, and that turns into ml dot. And then when you take the time derivative of ml dot, you get ml double dot. So then you have ml double dot is equal to ml theta dot squared plus mg cosine theta minus kl minus lo. And and dividing both sides by m, you get the equation for L double dot, which is dependent on theta dot, theta, and L. And then so for the second part of the equation, finding the motion by theta double dot, you start off with the left-hand side of the Lagrangian, which is the partial derivative of the Lagrangian with respect to theta. And you see that theta only pops up once in the equation at the very end, is minus mgl sine theta. And the left hand, and then the partial derivative of Lagrangian with respect to theta dot is going to be ml squared theta dot, because again that only is hitting this one term of the equation. And then, so when you take the time derivative of this, time derivative of that, L squared and theta dot both depend on t. So when you take the first part of you have to use the product rule, and you get m L squared theta double dot. And for the second part, you have 2ml, where the 2's coming down, theta dot, and then theta dot, hold on. And then for the second part, you have 2ml theta dot L dot, where you're first starting by taking the 2 from the L, and then you have to take the derivative of L with respect to time, which is L dot. And then so now you can put this into an equation, and which is right here. You have negative g L sine theta is equal to L squared theta double dot plus 2L theta dot L dot. And I'm pretty sure this is supposed to be positive sine theta, because, yeah, I think. And then when you rearrange this formula for in terms of theta double dot, you can rewrite it by moving this over and dividing by L squared, and you get theta double dot is equal to negative g sine theta divided by L minus 2 theta dot L dot divided by L. So one place I thought that this could be used in, or like one application of this that I was thinking of is if you're golfing and you want to try and find the shortest path from a ball to the cup and you're putting, you can use it using the Euler Lagrangian method.